Simpson's 3-8 rule is another rule of the Simpsons which uses the third order Lagrange polynomial. And you can see here, instead of using this function, the actual function, we are using a third order Lagrange polynomial. And when we use that, the final integration formulation becomes like this. And for a third order polynomial, we need 4 points. And from these 4 points, the first one and the last one are the limits, a and b. And these two are in between. And we actually are dividing into equal h value, equal ranges, let's say. And this is actually h is b minus a divided by 3. So we have 3 segments, but in one formulation. In one single application of Simpson's 3-8 rule, we have 3 segments. So this is similar to 1-3 rule, but it has third order polynomial. This equation is called 3-8 rule because of this 3 divided by 8 in the beginning. And hash is, yes, this hash is multiplied by 3 by 8. And this is the third Newton-Cotes closed integration formula. The first one was trapezoidal rule, which was using the linear polynomial. The second one was Simpson's 1-8 rule, which uses the second order Lagrange polynomial. And the third one is the Simpson's 3-8 rule. It uses the third order Lagrange polynomial. It is also expressed in the form of b minus a. When you replace this here into h, b minus a divided by 8, and here there is 3, and here there is 3. These are cancelled out, so there is no 3. And these are the function values of the 4 x values. And the error term of 3-8 rule is given by this, which has a fifth order of h and a fourth order of derivative, which is similar to the Simpson's 1-8 rule, which is using a second order, a lower order polynomial. So the order is the same. Only this value is a little bit different. This is smaller. That's why the error here is smaller. But because these order magnitudes are the same, the magnitude of the error becomes the same for both Simpson's 3-8 and 1-3 rule. And because 1-3 rule is using a second order instead of a third order, actually that's preferred instead of this, because this is a more complicated formulation and error magnitudes are the same. Yeah, it says here the order of error is the same as 1-3 rule, hence the error magnitudes are similar. The denominator of 3-8 rule is larger than for the error of 1-3 rule, so this denominator is larger. It was 2880, I think, for the 1-8 rule. This is larger, but the 3-8 rule is somewhat more accurate than the 1-3 rule because of this larger denominator actually. But in terms of magnitude, they are the same. So let's see the Simpson's 3 rule in an example application in the following slides. Before showing an actual application example of Simpson's 3-8 rule, we can have an understanding of 1-3 and 3-8 rule together. We can use them together actually, because we said that the Simpson's 3 rule is usually preferred method because it attains the third order accuracy with 3 points and with a second order polynomial rather than the 4 points and a third order polynomial for the 3-8 version. However, the 3-8 rule has utility when the number of segments is odd. So we said that the Simpson's 1-3 rule is applied only for even segments, even number of segments. But when we have an odd number of segments, then we need to use 3-8 rule. So that means that we can use them combined in a certain integration area. For example, on the right hand side, you can see our example Ch21, and in there we used Simpson's rule to integrate the function for 4 segments. If we have 4 segments, then we can use 1-3 rule, no problem. But we can have other options as well. When we have 5 segments, for instance, we can divide it instead of 4 to 5. Then we cannot use the 1-3 Simpson's rule because it requires an even number. But instead we can say that, okay, for the first 2 segments, let's use 1-3 rule because 2 means even. In the last 3 segments, let's use 3-8 rule. You can do also like in the first 4 use 1-3 and the last one use 3-8. So you can play with it. Which one gives more accurate result, you can see that by changing them. And this way we could obtain an estimate with third order accuracy across the entire interval, because both 1-3 rule and 3-8 rule are in the third order, has the third order accuracy, because we said that 3-8 rule is already using the third order polynomial, but 1-3 rule, although it is using second order polynomial, it has a similar magnitude of error as the 3-8 rule. So both of them have third order. So this is a good match, good combination of the rules.